Hello, everybody. Welcome to the Luniverse. I'm Dr. Charles Liu, your host, and as many people around the world have already been doing for quite some time, call me Chuck. As always, as you can hear in the background, our co-host is with us today, Allen Liu. Hey, Allen, how's it going?
Hello. It's going pretty well.
Have you breathed any sighs of cosmic catastrophe relief lately?
Well, presumably we're talking about the asteroid 202 2024 YR4,
Yes,
which was had something like a 3%-ish something maximum chance of hitting us, and now that's gone down to basically 0, which is great.
Yeah.
That's what we were predicting.
Just as we had said on that short video that we had put together for the Luniverse channel, right? The probabilities go up and up and up, and then they go down to nothing, right, as we get better. Well, that's too bad. Well, no, it's great, but yeah. Might have gotten really excited.
Yeah, there was a while there where it was looking like it might have had a bigger chance of hitting the moon than the Earth. I would love for it to hit the moon. Yes. That would be awesome, because then no one gets hurt. No one gets hurt by it, but we get to see this big crater and everything. That would be awesome.
Yeah, it would. And it is our incredible pleasure to welcome today's guest, Dr. Melodie Kao. Hi, Melodie.
Hi, everyone.
It's good to see you. You are coming to us from sunny Arizona. As you can see, there's plenty of succulents in your background there. For those of you who are just on the audio instead of on the YouTube, check out the YouTube. You can see all this stuff live and
recorded.
Recorded, yeah. How does that work anyway? Live on a recorded. Anyway, hi, Melodie. Tell us a little bit about where you are, what you do, things like that.
Yeah, so I am an astronomer at Lowell Observatory, which is in this beautiful, beautiful little town up at 7,200 feet in Flagstaff, Arizona.
Fantastic.
So we've got a ton of sun, and also last Friday we got a big dumping of roughly 1 to 2 feet of snow. And nearly all of it melted away. Yeah, it's really beautiful here.
Wow.
And I joined the observatory almost a year ago as their resident radio astronomer. So it's an optical observatory, but I convinced them that they wanted a radio observer.
Yeah, nice.
And
that is very interesting. Yeah, because Lowell Observatory is famous for being the place where Clyde Tombaugh discovered Pluto back in 1930.
Yes, indeed.
And since then, it has been a center for astronomy research in America almost 100 years now, and now a radio astronomer. How exciting.
Yes, we're quite fond of Pluto still. So just a couple of weeks ago, we had our I Heart Pluto festival.
Hey, with the little heart on the Tombaugh Regio.
Yes.
Nice.
Wonderful. Well, we will talk a lot more about that in a very short time. But right now, we have to get to our joyfully cool cosmic thing of the day.
Yeah.
Right? Yeah. We always love that one. And this one is very cool. And it's quite relevant to finding planets and things like that, because there is a project that is going on right now on a telescope in Arizona. Kitt Peak National Observatory, to be exact. On Kitt Peak, there's a telescope called the WIYN, WIYN. You guys should all take a look at that. And what was so cosmically cool is they have been running a special experiment on there called NEID for a few years now, and they are producing amazing results. Most recently published, a result of a planet discovered around a sun-like star 49 light years away from Earth. That's about 9 times the mass of Earth, but has an orbital period of just a month, 31 days. This is a super, super cool discovery. I think that's really awesome. And the thing that makes it really super cool for me, you guys all please go look it up. The NEID Spectrograph is on, like I said, Kitt Peak National Observatory's WIYN telescope. And the measurements, I was reading this paper. They are looking, remember, at an object 49 light years away. Okay, that puts it at almost 300 trillion miles away from Earth. Okay, they're looking at a star that's almost 1 million miles across. And to find this planet, they were able to measure the velocity of the wobble of the star caused by the planet, a total amount of 3.5 miles an hour. Okay, that's like walking distance. I can't even see somebody like across a football field and tell whether they're walking back and forth. But this amazing spectrograph and the amazing astronomers that are operating it are able to tell that a star 30 trillion miles away or 300 trillion miles away is walking back and forth.
That's almost as impressive as you getting the Joyfully Cool Cosmic Thing title, right?
Thanks a lot. Thank you very much. But it is kind of true. Melodie, you are an expert in low mass star-like things, brown dwarfs and planets. I mean, what is your take on that kind of measurement, helping us to find Earth-like or almost Earth-like planets around all these amazing stars?
I mean, I remember as a grad student, one of my professors demoing to us just how precise of a measurement we'd have to make to discover Earth-like stars around, or Earth-like planets around stars like the sun. And he literally just like strolled across our classroom, and I think that was the moment that I realized that how much virtuosity is involved in everyday science discoveries like this.
Right. It is quite amazing, right? How we just hear in the news, even as an astronomer, I'll take something for granted. Oh, they just found a redshift 9 galaxy, or, oh, they just found an exoplanet around a star, blah, blah, blah. Yeah. And sometimes it just takes a moment to pause and realize how amazing both the technology to make the discovery happens and the carefulness and the dedication that our colleagues are devoting to making these discoveries.
It reminds me a little of a discovery I published just a year and a half ago, where I strung together 39 radio dishes across the northern hemisphere of Earth to make an Earth-sized telescope. So similar to the technique that imaged the black hole back in the day. So I did that, and I pointed it at a brown dwarf, which, for those of you who aren't as familiar, brown dwarfs are teeny, teeny, tiny, almost stars. They're not massive enough to burn hydrogen, and they're a little bit too big to count as a planet. So we're talking something that's the radius of Jupiter, and which is roughly 1/10 the radius of the sun.
And 10 times that of Earth.
And 10 times that, and 10 times that of Earth. And I pointed this giant telescope at this little brown dwarf sitting in space, and resolved out what we call radiation belts around the brown dwarf. So there are things called Van Allen belts. They were the first discovery of the space age, and every time we send astronauts, or every time we're going to send astronauts to the moon, we're going to have to avoid the Van Allen belts. When we send things to Jupiter, we have to orbit around. We have to orbit up and down. Basically, all of the magnetized planets have these crazy energetic donuts of really high energy particles around them.
Yeah.
And a team of us thought that maybe we could do this for an object outside of the solar system.
Amazing.
And essentially, that was what we did. Was we imaged the magnetosphere of a brown dwarf that was 24 Jupiter radii across.
Whoa.
And that was the equivalent of looking at something the size of a pea on the Golden Gate Bridge if we were standing at the Liberty Bell. And it didn't really quite hit me what we had done.
That's incredible.
Until we were trying to figure out how we could, why the image was so smeary. And then we realized that we had forgotten to take into account the motion of Earth orbiting the sun over a 5-hour period.
Oh, man.
And that was enough to smear it up.
That's crazy.
That's amazing.
Those kinds of measurements, or the measurement that then, how do you call it? The NEID?
NEID
that the NEID team,
the
kinds of measurements that the NEID team just published.
Wow,
it's a thing that we do every day.
That's impressive. I know with the Van Allen belts around Earth, you mentioned that they're the first major discovery of the space age. What I remember about this is that the Americans' first satellite, so Sputnik, which was the Soviet satellite, was the first satellite in total, but the first American satellite, Explorer 1, was the thing that discovered these radiation belts.
Yeah.
Wow.
Yeah, it was the first science, it was the first American satellite with a science instrument. So we sent it up into space.
Wow.
And the particle counter on it just went ballistic, and we didn't know what was going on.
Well, wait, why didn't Sputnik find it?
I think
did it just not have the instrumentation?
I think it didn't have the right instruments on board. I think it was Sputnik was really just a tech demonstrator. It had like a little bit of science with like its radio signals and things, but it was not really designed to find these things. And then the other thing about them in the space race is that you mentioned that they're a hazard to astronauts, right? So there's a whole thing where people are like, well, how did the Apollo astronauts deal with it when they were going out to the moon? And then some people say that means like the Apollo astronauts couldn't have gotten there. But really,
right.
The way that
there is a trajectory that you can plot to avoid the worst of the radiation.
Yeah. So they
but the fact that we discovered it made that possible.
Right. So had we not made those previous measurements, maybe they would have had a lot more radiation damage to their body.
The first few astronauts might have been, badly injured.
That's
amazing.
That's why you do science ahead of time.
I think that's fantastic. Yeah. We've had several guests who are experts on exoplanets and brown dwarfs lately on this podcast. And I'm very happy that we're doing that because it gives us a chance to talk in greater extent about these topics, which normally we only have a few minutes to devote to at a time. So Melodie, you're talking about the technical aspects of discovering, say, magnetic fields around brown dwarfs is really an opportunity that we don't get a chance to talk to as much as we'd like. You're pointing 39 different telescopes at this object at the same time. But 39 telescopes, they're like thousands of miles apart. So one is like aiming toward the sunrise while the other's aiming toward the sunset. And you've got to rotate and take into account these observations. That's not one person's activity, right? I mean, that's dozens, maybe hundreds of people.
Yeah, it was one of the hardest observations I've ever done. And actually to make it happen, so, I came up with the idea to do it, but I didn't even know how to use this particular observational technique. It's called very long baseline interferometry, and there are the National Radio Astronomy Observatory already has a flagship observatory that does this kind of stuff. It's called the Very Long Baseline Array because astronomers are very creative, quite literally by their name.
Yeah, well,
but that's just 10 dishes.
Oh.
Right. And then we added in the very large array, which is NRAO's like main gigahertz radio array. And
that's
then
where Jodie Foster climbed into the
and gigahertz means it's the frequencies around like your Wi-Fi.
Around your Wi-Fi, sadly, yes. Sometimes your cell phone as well.
Yeah.
Wow. So you added VLBI to VLA.
Yes. And then we added in Green Bank Telescope, which is this huge 100-meter dish in West Virginia. And it's so massive that when it slews, the whole thing will slump a little bit just under the force of its own gravity.
Amazing.
And then we added in one more 100-meter dish in Germany. So that was, a multi-observatory effort. And I had probably one of the world's experts in very long baseline interferometry teaching me how to construct these observations so that I could pull this off. And then each of the main people at the main schedulers at the observatories were talking to me and talking to Amy Midashevsky, my co-first author, sorting out when we could schedule these. So it everyone really pulled through, and it took so many tries to even get it done because stuff would break. If you're out over here, something breaks on Green Bank Observatory, then the rest of the observations don't have enough sensitivity, or the weather comes in over here and then you lose a whole bunch of data. And then COVID happens and some observatories are shut down, others aren't. So it was a really challenging
a true international ballet of scientific awesome.
And each telescope has its own calibration requirements, so it's almost like orchestrating this dance of telescopes around the whole world, and every so often they'd all sync up, look at the same thing for about 90 seconds and then look away and do their own little thing again.
Amazing. Okay, we have to create a movie or something. That's an Oscar winner for sure. Okay. Well, I want to get to a question from an audience member, but before we do that, let's take a short break. And we are here on the Luniverse podcast with Dr. Melodie Kao. We'll be back in just a moment. And we're back here on the Luniverse podcast with Dr. Melodie Kao, brown dwarf and massive radio astronomy observational expert. We have a question from our audience. Allen, tell us, who is asking us this question today, and what is that question?
Yeah, so these questions are coming from a high school in Tennessee, specifically North Green High School. So we appreciate all the questions that they sent in. And we are going to ask our first question from Ari. Ari is asking, so we, in the past few minutes, we're talking about human habitability in space. We're talking about finding planets and things in incredibly tiny wobbles. So this is sort of puts those together. So Ari's question is, what is the percentage of possible exoplanets that are similar to the Earth's atmosphere, placed in their solar system, like in the Goldilocks zone, etc., and gravity, and how long would it hypothetically take to get to them? So I guess this is about the questions for ones that have the potential for life, whether or not they actually do have life.
Yeah, that is such a complicated question. I know someone who's dedicated her career to studying exactly this question from many different angles.
It's a big one,
right? Because it was a multi-part question, and I think it kind of what's really interesting right now is that everyone was so excited about James Webb Space Telescope and observations of atmospheres on terrestrial planets using James Webb Space Telescope. And one of the running jokes in the astronomy community right now is that everything fits a flat line. That is, we don't quite see very much evidence of atmospheres right now.
Interesting.
And that's one of the big puzzles that we have, right? We were expecting to see all these atmospheres around rocky planets.
Yeah, because 3 out of the 4 rocky planets in our solar system have atmospheres, right? Like Mercury is the only one that doesn't.
Mercury has a very tenuous atmosphere.
Okay, that's fair then.
And Mars has an extremely, extremely tenuous atmosphere as well.
That's fair. It's like 1%
2 out of 4 then.
Yeah, I would say like Venus and Earth are the ones that have the meaningful.
That's fair.
But they haven't shown up yet in the JWST observations.
To my knowledge, no.
Wow.
And I'll asterisk that by saying I'm not an atmospheres exoplanet scientist.
Okay.
So this is what you hear down the grapevine from your other exoplanet colleagues.
That's fair.
But this question is it's one of the big golden questions. It's one of the driving questions for why we built an instrument like James Webb Space Telescope, why we were interested in why we have other instruments like the Express instrument on Lowell's Discovery Telescope, which is looking for Earth-like planets around a sun-like star, so that we can start to quantify this more.
I see.
And it's also, this question is the basis of the Drake equation, which which is a very famous equation. So
yes, absolutely.
If this student had asked this question before Drake had, then they would have an equation named after themselves.
Ooh, the Ari equation. Very, very neat. Wonderful. Okay, well, thanks. For giving us the latest. Bottom line is, until we find a good rocky planet outside our solar system with a good atmosphere, your question remains unanswered. Well, nevertheless, we will keep looking. And you said that just in your observatory, Melodie, just up the street and up the mountain, I guess, there is such an attempt to find these atmosphere-laden planets as well, huh? Pretty cool.
The actual planets themselves. And when we discover the planets, then people will go to James Webb Space Telescope. Yeah, we have one of the world's most sensitive radial velocity instruments called Express. And that was built by Deborah Fisher and her team, and they picked our telescope because we have such a large aperture, I should know this, a little over 4 meters, I believe.
All right,
this is the radial astronomer.
That's fair.
Right now.
That's fair. Yeah,
that's right.
In a sunny spot. But
your radio dishes are hundreds of feet across sometimes, so you can be forgiven if you forgot the 10th of a meter of an optical telescope.
That's fair.
But that's what our collaborators are for, right? Yeah. None of us individually knows everything. We want to have as many people working together as possible. Like I said, just that kind of design of experiments, the way that we sync up individual institutions to create these kinds of observations, I think is just lovely. And, this is a perfect segue for me to ask you something, Melodie, which I know a little bit, but our audience doesn't yet. You actually have a design and architecture background in addition to your physics and astronomy background, right?
Yeah, I started in architecture before I ended up in physics and astrophysics.
I want to know about that a little bit. Tell us, because, a lot of our audience, even me, right, have many interests in life before we sort of decide on one thing to do in our career. But those things that we are still interested over time continue to influence us and make us better in the careers that we choose. So Melodie, tell us a little bit about that. Like how, like that whole story, which I think is so cool.
Yeah, so it really all started with a book report that my fourth grade teacher asked me to write about Frank Lloyd Wright, who is a very famous architect. Actually, one of his main centers is down in Scottsdale, so just 3 hours away from where I live. And he was really famous for a style of architecture called prairie style. And I remember just totally falling in love with his work. So this is Melodie, age 9. And from that moment onward, the only thing I wanted to do was be an architect. So I would draw designs of houses. The early ones had trees coming out the center. Later on, when I was a grad student and I didn't have enough money, then I would design tiny houses for myself. Just so you can see how everything evolved over the course of my life. And I actually, when it was time to apply for colleges, I applied for programs in architecture and civil engineering. So I had no intention to ever get a PhD or study science, and especially because my dad was a professor, and so I was very much, many kids don't want to do what their parents do, so I very much didn't want to go down the academic route. And then when I showed up at MIT and started taking my studio classes, all of my math and science classes went away, and I didn't realize until the moment that they stopped just how much of a part of my life science, and in particular physics, really was. Like, I still remember the very first physics, the very first time I encountered Isaac Newton's laws and learned about every force generates an equally reactive force. And I just opened doors for, I think, 3 straight weeks, just seeing all the force vectors.
Awesome. Oh, wow.
Yeah.
That's
or like
great.
every step I took, I could feel my foot pushing the ground away and the ground pushing me. Mm-hmm.
That is so
and
cool.
all of a sudden, all of that was gone. And I was at MIT. They have a wonderful school of architecture there. They also are home to some buildings designed by another favorite architect of mine, I.M. Pei. And most importantly, the physics department had just finished constructing the Center for Theoretical Physics, which was this marvelous building, retrofitted an outdoor courtyard, and then constructed these floating stairs and spaces for people to gather and work out problems on the whiteboard. Yeah, and then just a glass ceiling on top. So they took an outdoor space and turned it into this really beautiful indoor space. And then they saved the entire first floor for a work of art. So every building at MIT, they set aside some percentage of the budget to commission a work of art. And in this case, it was a building-sized, it looks almost like a mosaic, but it's not quite. I think it's terrazzo, of just like a beautiful shapes and bright colors that just fill up the whole floor. Wow. And as an undergrad, I'd walk by almost every night trying to break into the building. And, and what really, the moment that I decided to give physics a try, there were 2 realizations. One of them was that any department that could build something so beautiful might be a place that I could find a home.
Cool.
And second of all, that the reason why I had turned away from physics and math my whole life was because I was intimidated, and I didn't think I was smart enough or good enough, whatever that means, to do it. And I was in the one place in the world where if I wanted to learn how to think like a scientist, then I had a good shot. So I walked into the physics department. I asked them if they would let me continue taking my architecture classes so that I could earn my minor concentration in architecture, which traditionally in the physics department, you do a minor concentration in something more useful, like electrical engineering or science.
Useful to physics, maybe, not necessarily useful to the universe.
I made my case for why I thought architectural design was relevant to physics, and they let me do it.
Awesome.
So I took my studios and my lab classes at the same time.
Wow.
And, over time, I struggled a lot in physics.
So did I. It's okay.
Yeah. In my statistical mechanics class, I was a student who for one of my exams set the curve for what was failing. I had the worst score. I cried so much.
It's the tail of the distribution. So
I cried so much.
Oh,
but every time I tried to walk away from it, I couldn't. And the reason was that there was just something so beautiful and so elegant about physics, right? It was almost like every class I went to, I could tell it was like the professor was telling me a story that I wouldn't otherwise know about the universe. And over time, what I realized was that architecture is a study of how humans interact with our built environment and how that changes our perception of ourselves, how we interact with our communities, with the other people around us, even how we build our lives, right? How we live our lives. And astrophysics and astronomy and physics is really about the interaction of how between humans and the natural environment, right? And how when we learn about something as spectacular as one of the big memories I have, the day I discovered that astronomy was a thing that I could do. I saw someone giving a talk, a grad student giving a talk about galaxy clusters, and she put up this image, a science image of a galaxy cluster, and explained to us how you could back out the formation history of a cluster of galaxies by looking at the gradients of colors generated by starlight. And like that was a moment that I realized not only do my professors in physics tell me secrets about the universe, but if I look hard enough and listen hard enough, everything around me, like the light that we gather, it's all of these stars, all of these galaxies are telling us their stories.
Amazing. That is utterly awesome.
Incredible. I love that.
And amazing. I often quote to my students Albert Einstein in 1930 when he felt that sense of being awed by the mysterious is the true root of all great art and science. And your story has just personified that in an amazingly beautiful way. That's awesome.
And the artistry comes out again, going back to the beginning of the conversation. We make these really precise measurements, but there's so much artistry in making that measurement, or even in designing the instrument that made it possible.
Yeah.
Right. So it's that sense of artistry just really permeates all of the science that I've done. And so the training that I had in architecture is, to me, it's the same thing as what I do in physics. It just looks a little bit different. The stories that you tell, the way that you observe the world, and how you tell the story that the world is telling you, and what you choose to focus on, and like instead of constructing a building, I'm constructing an idea. Right?
Wow.
And then we see where that idea goes.
Marvelous, marvelous, marvelous. Wow. I think we should go to a question from an audience member now. I don't have anything else to say but to find out what other people are thinking. Isn't it amazing? I mean, Allen, tell us. Who has a question for what?
Oh, man. It's just hard to follow up. Let's put it that way.
Yeah.
So I think I'm going to do a question here talking about sort of human experience maybe a little, and talking about how people sort of want to envision themselves in the universe. I think I'm going to ask Alex this question right now. Another high school student here is asking, what are the conditions necessary for life in the universe?
I mean, there are probably thousands, right?
Right.
But,
there's so much.
Pick one, Melody, that you think is, or a few, or some set that you think would be a really, thing that you think about. Think that you would, tell Alex to think about.
Yeah. So there was a really interesting class that I audited when I was a postdoc at Arizona State. And it was about the search for life on Europa, which is one of the places in our solar system where we think that there might be a chance for there to be life. Europa is a moon of Jupiter. It has a saltwater ocean underneath an icy crust. And in the very beginning, so we actually asked this question: what are the conditions for life? And when you take this question actually, you have to break it down a little bit more. And you have to ask yourself, what does life mean? And one of the things that came out of the discussion that we had was that part of what life, one of the markers of life is that there's some way for an organism to learn. So for humans, we learn, you see us learn all the time. We adapt to a changing environment. We get new information, and that weaves into the story that we tell of how the world works. A big challenge occurs, and we come together and we invent some new technology to help us grapple with this challenge. But if you go down to a simpler level, say you have a microbe, and it finds itself in an environment that is
challenging or something.
Challenging for itself, then how does it change so that it can continue to live and continue to thrive? Right? And that's a form of learning. And so one of the things that I really took away from this class was the question, what does learning mean? And when we ask ourselves what conditions are necessary for life, one of the questions we're really asking ourselves is, what are the conditions necessary for learning to take place?
Whoa. That's beyond my pay grade, that's for sure. Holy moly. I mean, to even think of how a microorganism or an exo being learns, from its environment or gains knowledge it did not previously have. I mean, that's so beyond just chemicals, right? And reactions. That's remarkable. Whew.
Yeah.
Wow.
For me, I don't know if we want to go into this deeper, but for me, that brings up the question of, like, if we're now claiming we can make machines that can learn, right? Our computers and things like that.
Right.
And I'm wondering, does that give them, are they somehow more alive than our other machines that like steam engine or something like that are just there?
Whoa.
That is such an enduring question that people have been pondering for so long.
Yeah.
Whoa, that's got to be a topic for a future episode for sure.
Definitely
wow.
a future episode
That's a
topic.
Great point, though. That's a great question, Alan. I love that point. Wow. There's so much cool stuff that we've been talking about today, Melodie. I think it's really great. I mean, you're talking about the interactions between us humans and made environments, like architectural environments, and then natural environments like the universe itself. Do you go and do stuff like interact with the world in a deep way that helps you further get this kind of amazing, like, insight on the research in the universe and the stuff that you're doing?
Yeah, so I would say that at a broad level, I've organized my life around exploring the natural world. Right, so on a day-to-day level, for the job that pays my bills and feeds my intellectual curiosity and creativity, I explore the natural world beyond Earth. And space, I very much think of space as a form of wilderness. Many humans haven't gone to space yet, but
it's true.
It is part of the natural world. There is so much that we don't know. Some of there are environments that we don't know. So space is very much a form of wilderness for me. And then there's another form of wilderness which is closer to home, which are mountains and canyons.
Yeah, you were just saying that your area of Arizona, right? It's got mountains and beautiful stuff.
It's so beautiful here.
And it's right near
Grand
Canyon or something,
hour and a
isn't
half
it?
from the Grand Canyon.
Yeah.
And so one of the things I got involved in as a postdoc when I was at Arizona State, I created a wilderness astronomy class with a very dear friend of mine, Park Lloyd, who was also my office mate. It was actually his idea, and he invited me to join him in creating this class.
Oh, amazing!
Yeah, and the university really threw their weight behind us. Our mentor, our postdoc mentor, Jenny Skolnick, really threw her weight behind us, and we created this a semester-long class for non-majors and novice backpackers, and we had a 1-week backpacking component.
Wow!
And the idea was that so much of science has become something intimidating, something about whether or not you're smart enough, whether or not you're good enough at math, whether or not you can do the problem sets, when really the very basis of scientific discovery and inquiry is just, are you enchanted by the world around you?
Yeah.
And are you curious about it? And are you brave enough to ask yourself and ask other people what's going on, even if you don't know what's going on? So we created a whole class that took out all the equations and just took students and put them into more of a physically intuitive environment where they could wake up one day and see condensation on their tents and ask us, where did the condensation come from?
Wow.
We would have them
awesome.
pretend. Yeah, we'd have them pretend to be molecules of air and, fast molecules that run around really fast, and then cold molecules that slow down. Right. And by the end of this week-long class, they were staring around and asking us about the greenhouse effect and how weather happens, right?
Yeah.
And we could walk them through the thought process and it all starts with, what did they observe? Astronomers at their hearts are observers, and so are scientists. We're all observers. So that was kind of what put me on the pathway to realizing that there's so much exploration to do back home. And sometimes when I spend all this time studying worlds so far from Earth, and sometimes I miss being back home, and I'll go out into the mountains. So as a postdoc, I ended up getting involved in guiding long distance off trail backpacking trips.
Wow.
Yeah, there's a whole mode of travel, a whole style of backpacking we call high routes, where you go really, really high, they get off trail, and you're just navigating with all of your senses and all of the knowledge that you have. And it just, what's so cool about it is that in research, we're sort of standing at the edge of human knowledge, and we don't necessarily know what it's going to look like the next couple of steps we take. Like, we didn't know what James Webb Space Telescope would show us, and we built it, and that allowed us to explore so much further into space. And similarly, when you're off trail, you don't necessarily know what the next thing is going to look like. Is it going to be a field of talus? Is it going to be tundra? Is it going to be a field of scree? Right? Like, is there going to be a cliff that you can't get off? You have no idea. And what you do have is trust in yourself and patience, and the ability to observe and make decisions, and the ability to be brave. And so I spend all this time, I spend all my vacation time guiding, partly because it's a form of teaching for me. And I think it's a really important form of teaching, where we teach people how to feel, how to deal with discomfort.
Wow. So no GPS, no cell phones, no technology.
I prefer analog. Yeah, I really like navigating without GPS. I still teach that skill because it's a really important skill in your toolbox. But there's something really empowering about knowing where you are at all times, or knowing that if you're lost, you can find yourself again. Right? And similarly in science, sometimes things will go sideways.
Yeah.
Or the field changes.
A lot of times things go sideways. Oh,
that's real.
Right. And so having the emotional capacity and the bravery to stay with it, right? It's the same skill as having the bravery to be in an uncomfortable situation outside and know that you are strong enough and you are capable and can go places that are beautiful and like worth seeing and cherishing and exploring, right? So it really,
it's amazing.
Yeah. And what it really comes down to is exploration, and how does exploration and curiosity and bravery weave together to create, a spirit of cherishing everything around us.
Amazing. You are a true explorer, Melodie. You're not just in science and the universe, but in art, architecture, and now like nature and stuff. That's so amazing. And it's so awesome that you are like that, right? That scientists are not one-dimensional. We don't just do equations all day, but we're really thinking about the big things and having so much fun doing it and really connecting deeply with our environment and things aren't in our environment. I think that's lovely. Oh, Melodie, this is so awesome. I would love to continue this conversation forever and ever and ever, but we're running out of time. I'm so sorry. Can you come back sometime? Can we talk more in the future? Because there's so much I think that you have to share with us that I would love to hear.
Oh, I would love to.
Thank you.
Research is always changing. Lives are always changing.
Right.
Yeah.
So right now, what are you doing at the moment that we can follow? And maybe if we can find you on social media or on the web or something, tell us what your moment by moment right now thing is and where we can find you.
Okay. So I am you can't find me on social media.
Okay.
Well,
okay.
I'm a little old-fashioned like that.
Okay. No, it's yeah.
I'm a little old-fashioned on that. You can. I do have a website that does need to be updated, but it is melodiekao.com.
Okay.
And right now, I would say one of the things I'm most excited about. There's a lot of interest in something we call star-planet interactions, which are planets that are interacting with the magnetic field and space weather of their host stars. And that can lead to all sorts of crazy, awesome phenomena like the aurora that we see on Earth, the aurora on Jupiter, all the radiation belts. And there was a recent discovery last year where another astronomer, Jackie Faraday, detected methane in emission from a very, very, very cold brown dwarf. It's about 458, I think, degrees Kelvin, maybe 457 degrees Kelvin.
Boy, chilly.
By comparison.
Yeah, very chilly. Very chilly. And the only way to make the methane emission is that there has to be something going on in its upper atmosphere to heat it up. And this brown dwarf is just hanging out in space by itself, so it doesn't have a star or anything to heat up its atmosphere. So she came to me and asked me, could this be an aurora? And it's a question that I am actively looking into right now. And
that's awesome.
In the next couple of months, I will have the results.
Wow. We cannot wait. That is so cool. Everything that you talked about is so cool, Melodie. It's been awesome. Thank you so much, everyone. If those of you on the audio only, melodiekao.com. Is that right?
Any of you, yep, that's correct. And any of you who ever find yourselves in Flagstaff and want to come visit the observatory or hang out with an astronomer who gets you really excited. I like to be a what I call a civilian sometimes, and I'll go be a tourist at my own observatory. So anyone who's in town wants to check out the observatory and hang out a little bit, and just let me know, and I'm happy to show you guys around.
Thank you. I will take you up on that offer for sure. Wow, what a wonderful episode this was. Dr. Melodie Kao, Lowell Observatory, thank you so much for being with us today.
Okay, take care. It's such a pleasure.
Our co-host, Allen Liu, as always, thank you so much.
Yeah, always glad to be here.
And for all of you in the audience, thank you for joining us for this episode of the Luniverse. If you like what you see and hear, please support us on Patreon. And as always, thank you for being a part of the Luniverse.